Hello, everyone. How are we doing today? We doing all right? For those of you who said something, I am feeling a little bit better than I was the last time we had class here. I don't want to be too optimistic quite yet, but I feel like I may have turned the corner with whatever was giving me such a hard time. So probably need a couple days on the mend, but I ought to be all right here before too long. So I'm pleased about that. And so let's get into what it is we need to be talking about here today. And that is ultimately going to be Bessel functions, but there are a couple of other details that I want to take care of first. Okay? So, one of the things that I had mentioned last class was this special form. Oops. Forgot a y double prime. Sorry about that. Here we have ax squared y double prime plus bxy prime plus cy equals 0. And this is known as an Euler equation. Okay? What's noteworthy about this particular type of equation is that if I rewrite it in terms of its standard form, that is dividing by that first coefficient, what we get is the prototype for what it means to be a regular singular point. I mentioned last time that we look at these two limits, and in this case we're interested in what's going on at 0, and we take x times this expression, and I'll go ahead and simplify it, and x squared times this expression, and because both of these limits are finite, we say that x equals 0 is a regular singular point for both of, or sorry, for this type of equation. All right? Now, this is important to us because it turns out that when we want to look at other, more sophisticated differential equations, the Euler equation is going to form kind of a starting point for us to construct the rest of the solution in those more complicated cases. So we're going to use this as a jumping off point. Okay? Now, if we were to go through all of the details in the two note sections for 5.4 that I mentioned last time, this is covered in a lot of detail. Okay? The brief write-up I just did on the other screen is right here. Okay, and there are a lot of different elements of things that all play in together with one another. The first is the derivation of how to construct solutions to Euler's equations in simple cases, which involves this t equals the natural log of x substitution and the derivation that we talked about at the end of last class. Okay, and where it goes a step farther is where we start wanting to talk about more sophisticated solutions beyond these types of problems. Okay, and that is where we get into it with this kind of expression here. Okay, now this thing, as it's written right now, does not look like an Euler equation. Okay, because it has this extra term here instead of just having a coefficient c like we had before. But what we want to do is we want to build a solution using the same kind of techniques that we did last time in our previous sections for this chapter, and try to get something that allows us to use Euler's equation as our jumping off point. Okay, so let's get into that, and I will show you how this all works, and then we'll do an example involving Bessel functions. All right, so we start off with this differential equation, and the idea is that we are going to assume that our solution has the form x to some power r, and r is allowed to be a real number. Okay, what it's not allowed to be is 0, because that breaks the way that this method works. But we assume that it's some non-zero value. And what we're going to do is we are going to take these types of expressions, differentiate them, and then plug them into our function. So we're going to compute y prime. I'll go ahead and rewrite this like this so it's easier to follow along with what we're doing. Okay, so we just absorb the x to the r into our exponent here. And now when it comes to taking the derivative, we bring the power out front, and reduce the power by 1. Okay? Now, we are not, this time, going to get rid of the k equals 0 term in the series, because we did that before because we knew it was 0. Here, since r is some non-zero value, the k equals 0 term isn't automatically going to be 0, so we leave it in the formal expression and then do our computations based on that. The same is going to be true for when we take the second derivative. Again, just differentiating the power series notation like we have before, except it looks a little bit more complicated because the exponent is a little bit more complicated. All right. Now, it's a matter of plugging this into our differential equation. So we get 2x squared times the sum from k equals 0. And then we can just copy and paste all this. And then minus x times this. And then lastly, plus 1 plus x and the sum from k equals 0 to ak x to the, oops, k plus r, and this all equals 0. All right. So we have this big expression here, and we want to work all of this out so that everything combines together. We're going to add 2 powers of x to this exponent here. So it's just going to be k plus r. I'm going to add 1 power of x to this exponent here, so it's just going to be k plus r. And then for this, I'm going to end up with 2 separate sums and then have to work to combine them together. All right. I'm going to go ahead and pull the 2 on the inside too for this first term. It's very tempting to try to do multiple steps at once here, but we'll take it easy because I know there's a lot on screen. All right. Now for this part, I have done 1 times this sum, which is right here. And for the next part, what I'm going to do is I'm going to take x times this sum. So it's going to be the same thing except have an exponent of plus 1 here. All right. So that's a whole lot of stuff. I want to pause here for a second and make sure that everyone is following along okay. Please give me a yes or a no, at least a couple of them, so I have an idea of how people are feeling. Okay. I see that someone has a question. Please get that typed up so I can try to answer it before we keep moving here. Okay. All right. The question has to do with why, when we took our derivatives here, we didn't change the origin point of the summation. The reason has to do with this x to the r factor. Previously, we had summations that look like this. And when I took the derivative and got y prime, I could write this okay. But when k was equal to 0, this would equal 0, so that first term would be 0. And to not be confusing, we just wiped it away by changing the index. For these factors, I have this x to the r here, okay? And the presence of that x to the r gives me this factor, which isn't going to necessarily be 0 when k equals 0, which is why this stays. I don't change it. Okay? All right. So now that puts us in a position where these sums are easy to combine, but this thing I still have to play around with. Okay? Because it doesn't have the x to the k plus r. And so what we're going to need to do here is for this term is rewrite it splitting off the k equals 0 term. So we're going to get a naught x to the r plus 1 because k is equal to 0. I'm sorry, excuse me. I skipped a step. What we need to do is we need to reduce this index, which is going to increase this index. I have to do that first before I split off the term. Okay. And so what this will become is the sum starting at 1 now. And we're going to have a k minus 1 x to the k plus r because that has been reduced by 1. All right. The rest of this stuff gets copied down. All right. And now we can, since all of this stuff we want to combine everything into one sum. But we notice, of course, that all of these start at k equals 0, and this thing starts at k equals 1. So we have to peel off the first term from each of these first three summations. So we're going to get 2 times r minus 1, a0, x to the r, minus r a0 x to the r plus a0 x to the r and that's going to leave me with k equals 1. And now that I have k equals 1, I'm going to combine all of the rest of this into one sum. So we're going to get 2 k plus r minus 1 minus k plus r plus 1 a to the k this is kind of a complicated expression. Plus ak minus 1 x to the k plus r equals 0. Okay, and what I did was just collect this coefficient, then this coefficient, then 1, which is the coefficient here, and then put that all there. All right. So I recognize that this is a little tricky, but the idea now is that we condense this expression and also this expression, or at least we'll set things up here. Let's do one thing at a time. We see that a naught x to the r is going to be factored out of each of these terms. So we'll start by factoring that out. And that leaves us with 2r, r minus 1, minus r plus 1. Okay. And if we multiply all of this out, that's going to give us 2r cubed minus 3r plus 1. And that expression factors. Okay? So, this part here on the left is what is known as the indicial equation. The indicial equation, we care about when this is equal to 0. And we see that we get r equals 1/2 and r equals 1 as the solutions to this indicial equation. The roots that we get for the solution to this equation are known as the exponents at the singularity. And these exponents at the singularity tell us what values of r are valid for the solution to our differential equation. Okay? So this part right here, if you look at it and work it out, will give these exponents at the singularity. Okay? And it turns out that this stuff right here is all very closely related to the Euler's equation stuff that I was talking about before. Okay? For each of our differential equations that have regular singular points, and we're assuming that 0 is a regular singular point for this problem, you will end up with something that looks like an Euler's equation, and the indicial equation is exactly the same kind of characteristic equation that arises for an Euler's equation. So that's the point of the connection between the two of these things. All right? Now, once we have our exponents at the singularity, what we can do is we can choose one of those exponents and then start to determine the values of our coefficients by employing the recurrence relation given from this. Okay? So let's go ahead and write down the recurrence relation while it's on screen, and then we'll copy it down here in a second. All right. Now, we're going to want to do some multiplication of this denominator here to give us an easier expression, but we'll do that on the next page. All right. So let's work all this out here. Let's leave the 2 by itself, then we'll get k squared plus kr minus k, and then plus kr plus r squared minus r, and then minus k plus r plus 1. Keep going here. We're going to have 2, and then k squared plus r squared plus 2kr minus k minus r, minus k plus r plus 1. Why does it feel like I messed something up? All right. Sorry, I'm trying to track down what went awry here. All right, if we distribute the 2, what happens here? Okay. Alright, sorry about all this. There's an easier way to do this factoring, and I'm losing time. Okay, what we can do is this term here can be split. Is if we allow the 2 to go into this factor here, then what we end up with is this. And then that minus sign with the factor of 2 allows us to pick up these two terms here. And get this expression, which looks like this expression here, which is what I'm sorry. Which, after I fix my copy mistake, looks like this expression here, which is what it should look like because it's has the same form. And what's important about that is that this factors just like the other expression that we had previously. All right. Now, with this more condensed expression for the recurrence relation, the next step in the process is that we need to pick a value for r. Okay? Now, the whole point of our work with the indicial equation on the previous page was to allow us to determine what those exponents at the singularity are. So the idea is that one of our solutions is going to be for one of the exponents of the singularity, and the other solution will be for the other one. And so what we do is we write down the recurrence relation, choosing the value for r. In this case, we're going to set r equal to 1. And what that's going to give us for the recurrence relation is this expression here. Sorry, I wrote r. I should not have done that. sorry. For some reason, my brain was doing k equals 0, which was wrong. Or r equals 0, which is not what I wanted to write. Okay, so we set r equal to 1, and we want to simplify this expression. And so this becomes our recurrence relation for when the exponent of the singularity is equal to 1. Okay? Now what we can do is, starting with a 0, figure out what our values are here. Okay? So we can figure out a 1, and then we can figure out a 2, and then we can figure out a 3, sorry, that should be 7 times 3. And I'm grouping terms in a way that is going to be conducive to finding the pattern. And so what this allows us to say is that we note that this part here is just k factorial, and this part here looks like the product of all of the odd numbers up to 2k plus 1, because 2 times 3 plus 1 is 7. And so what this allows us to do is write down the pattern for the kth coefficient as negative 1 to the k power times a naught, and then we have to do the trick with odd numbers. The product of the first 2k plus 1 odd numbers looks like 2k plus 1 factorial over 2k, or sorry, yeah, 2 to the k factorial. But since this is in the denominator, what we end up with is sorry, 2 to the k factorial divided by 2k plus 1 factorial. This is for the product of the odd numbers part in the denominator, so that's why I took the reciprocal. We have also in the denominator k factorial for this part. Those two things are going to divide out. And then we have a naught and -1 to the k power. So simplified, this looks like -1 to the k power, 2 to the k power, a naught all over 2k plus 1 factorial. Therefore, our first solution looks like x times this series. Okay? Or you could write it as because technically this relationship doesn't kick in until n greater than or equal to 1. We would write it like this. Okay. And then note, here I wrote the x out front, but here I absorbed it into the exponent. All right. So I know that's quite a bit of steps. And the idea behind all of this is that once we put in the work, we will have our power series solution for all of this and be able to look at the first fundamental solution for this particular differential equation. In order to find the second solution, we follow a similar process, except we set r equal to 1/2 and then repeat the work that we have done here in order to construct the other solution that goes alongside. So what that does is it changes our recurrence relation because we change the value for r, and then we go through, we do some more work, we find more patterns, we find that the pattern is fairly similar to the one that we had before, just and there's no guarantee that the pattern would be similar, but in this case it happens to be. We come up with a very similar looking condensed expression to what we had in the other case and get a similar solution. Okay. We can plot it as well, and it has this kind of funny shape to it, but that's the idea. You work the problem through. I'll come back to this screen in just a second, but you work the problem through, using this method, which is very similar to what we had prior, except we just change our guess so that instead it looks like x to the r times a power series. And then you will eventually get to a point where you have some number of terms that need to be peeled off at the beginning. And these set of terms that need to be peeled off at the beginning will form the indicial equation. And the solutions to the indicial equation are the exponents of the singularity, which you use to define the recurrence relation one at a time to be able to find the two fundamental solutions to the differential equation. All right. Does anyone have any questions about that process? Yeah, I do know that this is quite a bit of stuff to try to absorb. Okay. It's part of the reason why the notes are written up like they are, so that you have a source separate from the textbook that goes through and really tries to show each of these computations and all their steps. So there's this full example that I've been covering that's gone through in full detail. So please read through these. Okay. And what I wanted to do by showing this first example here was to set us up to be able to talk about this example for Bessel functions, and to go through at least one of these cases so that you get an idea of how these techniques apply to this situation here. Okay? Now, before we get into the Bessel function stuff, there is one thing that I want to mention, because the Bessel functions have use a technique that is covered in the sections that in the textbook that I don't think are terribly well written, to try to pull things together. And then I will also say, please be nice in the chat. No need to pick on people. You're allowed to pick on me, but you're not allowed to pick on your classmates. All right. Okay. So for differential equations that fit into the mold that we are discussing here, specifically regular singular points, one of the ways to think about them is imagining that they are in this form here. Okay? In this form, what we want to imagine as going on is take special look at these two expressions here, and we're going to imagine that both of these are analytic functions. All right. So for these two functions, we assume that they have these forms, and if we assume that they conform to this expression, what we're allowed to do is talk about the coefficients that are associated with each of these factors. And we can make up some theorems that care about these coefficients, P0, P1, P2, Q0, Q1, Q2, and so on, where of course we are assuming that this thing looks like Q0 plus Q1x plus Q2x squared, and so on. Same thing with this function over here. P0 plus P1x plus P2x squared. Okay? So, in sections 5.5 and 5.6, which are in the online notes kind of wrapped up all into 2 pages, both labeled 5.4, we use this notion later on, okay, in that write-up. This is important because if we want to talk about a Bessel equation, a Bessel equation is a differential equation that has this form. Okay. This is the Greek letter nu, and it identifies what is known as the order of the Bessel equation. All right. Now, what this means for us is that I look and I compare these expressions to what's going on in the lines above. Okay? So if we start with this and compare it to this, we notice that we have x, which matches that x there, and then what must be an implicit 1, which is equal to x times p. Okay? What that tells me is that for the Bessel equation, x times p is equal to 1, and that means that the power series for this expression looks like this. So p of 0 is equal to 1, and then pk is equal to 0 for k greater than or equal to 1. All right? When it comes to constructing the solution, this is going to end up being important for us. Okay? Likewise, we examine this expression here and compare it to this thing here. Now, I don't have any leading term here, so this whole thing ends up being set equal to x squared q. And so x squared q is equal to x squared minus nu squared and what this tells us about the power series is that we have minus nu squared plus 0 times x plus 1 times x squared plus 0 times x cubed, and so on. So q naught is equal to negative nu squared q1 is 0, q2 is 1, and qk is equal to 0 for k greater than or equal to 3. All right. Now, in general, the ways that we construct solutions for these sets of differential equations can get very complicated. All right. And the general procedure involves utilizing these coefficients from the functions in the differential equation to help us construct the solution. All right, that's why we go to the trouble of identifying these coefficients. Now, fortunately, in these cases, the polynomials that we have that define these coefficients are low order, which means that the higher order terms in the polynomials are all 0. So they vanish. All right? And because these terms vanish, we can much more easily figure out what the solutions to the equations are. Okay? Thinking about the functions in the differential equation in terms of breaking down the function coefficients in terms of their power series like this as well, have a side benefit when it comes to the indicial equation. If you look right here at this line, this top line here, this formula for the indicial equation holds for all differential equations that sort of look like Euler equations. So all of the types of stuff that have regular singular points, the indicial equation is always going to be like this. Okay? And so that means that it is even true in the example that we did earlier, where we worked through and got this indicial equation. We had 2 here for the coefficient in front of r, which comes from the a. We have negative 1 as this coefficient here, and then also for q naught is 1. And if we look at our differential equation here, that's exactly what we would get from this expression. P naught is negative 1 because I have to take out this x in this expression here. And then for this, q naught is 1. So if I think about this expression here, as 2 because of the 2 in front of the x squared, negative 1 for p naught, and positive 1 for q naught, I get exactly the same expression as from the indicial equation there. on this screen. All right, so if you want to think about it in terms of this direction, there's a bit of a shortcut available. If you just need to find the exponents at the singularity, you can use the analytic form of the differential equation to write down the indicial equation. All right. Now, I do not believe that I will be able to jot all of this derivation down by hand in the remaining time that we have. So what I'm going to do is I'm going to use the notes here and talk through it. This is a slight variation on the process that we have done previously, but it is using the other half of the 5.4 notes and following along with a specific example. Okay. What goes on here, as you can see, is color-coded as extremely as it can be to make it easy to follow along with, because there's a lot of refactoring and moving parts. Okay. But I want to talk about the more applied version of this, because you will likely actually interact with Bessel functions. So we start with the Bessel equation, but what we want to talk about are the Bessel functions of order 0. So we set the new value here equal to 0 and come up with this much simpler version of the differential equation. All right. We use the stuff that I was just talking about in order to come up with the values for P naught and Q naught for the indicial equation. P naught is 1 and Q naught is 0 because nu is equal to 0, and we said that Q naught was equal to negative nu squared. This leaves us with r squared. All right. And so sorry about that. Didn't quite catch myself that time. Both exponents of the singularity are 0. And what that means is that we can have, we're going to have two separate solutions, but we'll have to use a special formula to get the second one to avoid the issue of linear dependence. The first solution is going to look like 1 plus the sum from 1 to infinity of these coefficients times x. And this is going to be our recurrence relation with 0 plugged in for the exponent. Okay? Now, for solutions of this particular form, we're always going to have a set formula for the recurrence relation. Okay? It turns out that these problems have a complicated but explicit formula for the recurrence relation that always works that we can use. All right. What we do is we take this sum, and this sum depends on those coefficients that I was talking about for x times p and x squared times q, and then also the previous terms in the recurrence relation. And then we divide by the indicial equation evaluated at r plus n. Okay? So we go through here and This serves as a reminder of what x times p and what x squared times q looks like for this particular differential equation. We have a very small number of non-zero values, only 2. P0 is 1 and Q2 is 1. Everything else is 0, which means that most of these expressions are going to be easy to compute. Okay? All right, so we go through here, we plug in values, and we can see that the computations here using the formulas, because there are so many zeros involved in the computations that come up, most of the terms are pretty easy to deal with. Okay? Now, as it turns out, this is simple enough that we can come up with a general formula. Okay? All of the even coefficients are going to follow this nice form, and the odd coefficients are all going to be 0. And by doing a little bit of extra work and finding patterns like we had previously, we will end up with this expression here, which is the definition of a Bessel function of order 0. Okay, it is the Bessel function of the first kind of order 0. These things have fancy names, all right? And so what we can do with all of this is use this series expression here in order to construct this series of functions that goes through and does a better and better job of approximating the actual Bessel function. The Bessel function itself, you see, is the curve that follows along here. Okay, and as I add more terms to the partial sum, we get closer and closer approximations to this. It turns out that you can use the ratio test to show that the radius of convergence of Bessel functions is infinity. So the more terms you add, you will eventually create a perfect reconstruction of the function for all x greater than 0, which is nice. And then we can go on from there. Okay. So I know this is quite a bit to take in, but I do want you to have some familiarity with these things because, especially if you are on some sort of engineering track, this class of functions are extremely likely to be mentioned again. All right. Now the second derivation for this starts with a different form, and there are a different set of computational rules that we'll need to use in order to compute the recurrence relations. Yes, this is a derivative. So we're going to need to differentiate with respect to the value r in order to get all that put together, right? And there's a cute little computational trick that's used here in order to generate a formula for this. Okay, and what we end up with is the Bessel function of the second kind, which has not as nice looking of a formula, but it is linearly independent from the first, which is what we need. And in applications, they don't use exactly the one that arises from the differential equation. they have a normalization factor that they apply to it in order to rescale the function in a useful way, but it has the same property here that we can come up with a linear combination of these things and approach the actual solution, which is the one that, of course, looks like it continues on and the oscillations here. Okay? And so plotted together, those two functions look like that, and notably form a very, very good basis for representing radial waves or vibrating membranes. So if you have like a drum head or some shape like that, this will tell you the amplitude of the wave away from the center point, which is the x equals 0 value here. All right. Okay. So a couple of things before we close up the lecture for today. Number one, I know that the computations for these last couple of sections are very involved, okay, and to the point where it's almost impossible to do them without having some material with you to reference, okay, some procedure to follow along with. I do not intend to ask you to do the full set of computations, especially for something like the Bessel functions without help. Okay, that would be a quiz question, not a in-person exam type inquiry. What I do expect you to be able to do is, when you're working these things out, be able to get to this point where you can isolate the indicial equation, figure out the exponents at the singularity, and then go through and perform this kind of work of being able to determine a pattern in the coefficients. Okay? So that's, and even this, of course, would be a pretty long exam question. And due to the fact that we still have a whole nother chapter to cover, we will figure out what is appropriate for exam type questions. But I will give a quiz. I'll post the quiz tomorrow afternoon probably for you to take a look at, and then there will be time for us next week, if there are questions, to figure some of this stuff out. Next week we will be transitioning to speaking about a new chapter, which is going to be a big departure from what we've been talking about this week in terms of material and stuff. It's going to be based on integration instead of being based on series. So we'll have kind of an abrupt change there. But I do know that this is kind of a lot to absorb, so if we need a little bit of time and need to do a little bit of discussion next week, that's perfectly fine with me. All right. So are there any questions before we close up shop here today? All right. I do hope that everyone's feeling okay. I know that there were a couple things in here that might have seemed like a bit of a barrage. But anyway, I'm not seeing any questions. I do thank those of you who are giving me the well wishes. I am feeling a little better than I was the past couple days, so hopefully I continue to improve and things will be going well by the time next week rolls around. So thanks again. Take care, everyone, and I will talk to you next time.